Hello, in this video I'm going to go over an OCR maths mechanics problem about moments. It's about a wall-mounted light. It's given us all the kind of information. It's like a modelling question. It tells us various things. For example, that the light, this lamp at the end, is modelled as a particle, and that has got mass 0.5, so it's got weight of 0.5 g. It's also talked about the actual thing that it's, the thing it's being mounted on has been modelled as a light rod, a uniform rod, and that has got of mass 0.25 kg, so of weight 0.25 times g. And it's got a hinge here. We won't need that for the next part, but it's hinged today. And there's also a kind of tension in this chain, also modelled as this chain is modelled as a light inextensible string. So it's called a tension in that T. And because this is 0.4 here and 0.4 here, we can easily see some of the angles as well, should we need them. For example, this angle here, that angle there's 30, that angle's 30, so the whole angle to the horizontal is 60, and various, we can play around with that a little bit as we go through the question. Now, let's get on with the question then. I think I've marked on all the forces. Kind of helpfully in this question, they've told us to take moments about A. To be honest, I'd have probably taken moments about A anyway, because it's often a good idea to take moments about the hinge, but it's told us that, so it's made life a bit easy for us. We know that we have to take moments about A. No point in taking them about anywhere else. It wouldn't be anyway, in my view, on this. So to take moments, remember moments is force times perpendicular distance. So I'm going to mark on the perpendicular distances here. We've got this distance here, which is the perpendicular distance to the centre of mass of the rod, which we can see the triangle is there. So that will be 0.4 sine 60. Likewise, because this is obviously going to be double that distance, this is 0.8 sine 60. Now the perpendicular distance to this, well, let's just draw this triangle here. It's going to be this distance. And that distance there, well, looking at it, we can see that this angle, this angle here is 60, and this angle is also 60. So that perpendicular distance there will be 0.4 cos 60. Which is actually equal to 0.2, but I'll leave in the ratio just for consistency. So it's 0.4 cos 60. Now we can see that the T is kind of pulling in the opposite sense, is kind of rotating in the opposite sense. The T is actually going anti-clockwise, and the other two would be going clockwise about A. Clockwise. If the rod were, imagine that the weight, this was the only force on it, it would tend to rotate that rod clockwise, as would the 0.25 force would tend to rotate it clockwise, whereas the T would tend to rotate it anti-clockwise. So that enables us to set up our moments equation. Moments about A. Remember, force times perpendicular distance, so that's T times perpendicular distance, which is 0.4 cos 60. And then we have take away the moment of this force, which is 0.25 g times 0.4 sine 60. Take away the moment of this force, which is minus 0.5 g times 0.8 sine 60. And that all comes to be equal to 0. Right, well, we know that cos 60 is a half and sine 60 is a square root of 3 over 2, so it shouldn't be too much bother here. That's going to be this t times 0.4, that's t times, or we could divide by 0.4, couldn't we? Divide by 0.4 and divide by cos 60. So if I divide by 0.4 cos 60, whichever way, I'm sure you can easily get there to where you want to be. So that's t. Let's take it to the other two terms to the other side. That would be equal to 0.25g tan 60 plus 0.5g times 2 tan 60. Tan 60 is the square root of 3 over 2, is equal to square root of 3, should I say. So this is going to be 1.25 the square root of 3, or 5 over 4 the square root of 3 g, which comes to 21.2 newtons to 3 significant figures. But I'm storing that in the calculator anyway, because I'm going to need it in the next part. So that's the first part. Okay, so let me minimize that and make a bit more space for myself. So now it is talking about, for part B, the force on the hinge. Okay, generally speaking, there can be exceptions, but generally speaking, it's a good, doing the resolving equations is going to be easier than moments equations to work out the other stuff. Let me rub out some of this stuff now so that I've got a bit of a tidier diagram, or at least some of the things on there. Can go now. Okay, let's take that distance out as well, although it was useful for our moments equation. Okay, so we've got y going upwards. Now, in fact, when we come to actually work it out, the force on the hinge kind of tends towards downwards. When I looked at it and I did it, I actually put it upwards. It's not a big problem here because y will just come out as negative in our equations. It's not always obvious to see. Reflecting back, I could see why the force would tend to be downwards on here, because obviously it's kind of being held in the middle with quite a hefty weight in comparison to the rod at the end. So it's kind of would be tending to push it downwards. But let's just go with it. I've put y upwards, it doesn't matter. X definitely has to go in this direction because it needs to counteract the t. Now, if you remember this angle here, that angle there is 60. Mark it in red. That angle there is 60 degrees. So we can resolve horizontally. Okay, so resolving horizontally gives me x equals t cos 60. Now cos 60 is equal to half, so x is, we already have what t is. X is equal to, that would be 5 over 8 the square root of 3g, which is approximately equal to 10.6 newtons, but make sure we've got a precise answer stored, because we want the overall force on there, as you'll see in a moment. So that's our resolving horizontally equation. It's given us the horizontal component of the force at the hinge. Resolving vertically, as I say, we've got y going upwards. We've also got the component of the t going upwards. Now that component there will be equal to, knowing how to resolve is a good thing, as we've done a lot of work on this. So that's t sine 60, because it's away from our kind of marked angle there. We've kind of got space there. So it's t sine 60 upwards. So y plus t sine 60. Okay, that equals to 0.25g plus 0.5g. So y equals to 0.75g minus t sine 60. Now working that out, I get the answer minus 11.025, which just alludes to what I was saying earlier. The actual force, Y, is the force there is actually downwards. So let's just mark that in. So basically we've got the component here, which we've worked out is that bit there is 5/8 square root of 3g, or 10.6 newtons. That's our vertical bit, the horizontal component, and our vertical component is actually downwards 11.025. So we want this bit here. So we can just you do a bit of Pythagoras on that. So force on hinge equals to the square root of x squared plus y squared, which is equal to the square root of 10.6 blah 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 squared, making sure you use exact, plus 11.025 squared, and that comes to 15.3 newtons. Okay, that's the magnitude of the force exerted on A. Okay, let me do a bit more tidying up. So that gives us, that's actually the first part of B. We want the second part is to find a direction, and we can mark, as long as we're consistent and we say what direction, I can mark that angle theta on there, and then I can just do a bit of trigonometry again. I would then have tan theta equals to opposite over hypotenuse, so that's my 11.025 over my 10.6 rounded answer there, and that comes 50 equals to 46, let's go to the mark scheme, actually 46.1 degrees. Okay, but we do need to describe it because, of course, we've got to acknowledge the fact that it's downwards to the downwards horizontal. Otherwise, we'll lose a mark if we do. If we just give an answer, we need to be clear what answer it is. It would be okay if you actually said this one to the downward vertical, as long as you describe it. But it needs to be described what angle we're actually given there. So 46.12 towards the downward vertical. So and it's downwards because in my equations I had it upwards. So it's got to be downwards. Okay, don't deliberate. Obviously we try and get it the right way around to where we think it is. But if there's more than a few components, sometimes it's easy to get it the wrong way around. In which case it'll just come out as negative, and we can just work with it that way. And then there's the very common modelling question, improvements. Well, what did it talk about? The rod being uniform. Talked about this being modelled as a particle. It talked about this being modelled as a lighter inextensible string. So we can mention any of those things and probably more. But what I wouldn't be doing is just going for the scattergun approach and just saying everything, because it says suggest one. So don't give any more than one, because if you actually start saying things that are wrong, you'll be penalised even if there's things that are right on there. So there's the here it says any valid improvement. Consider the dimensions of the lamp. So consider the lamp is not a particle basis. So consider the weight of the chain. Model of rod is non-uniform. Friction at the hinge. And they actually accepted more accurate value of G, but I would avoid that normally because it's not always accepted for, they must have had to think about the particular situation where they allowed that, but I've seen it not allowed in other examples, so I'd avoid that. Okay, so that's the end of that video. November 20. Again, it wasn't the easiest, some kind of average type difficulty questions. There will be some that are coming up in future videos that are more difficult than that. Okay, hope you found it useful. Bye.